and all the distinguished gathering here. It's really an honor to be told by Shri Kumar to come over here and be part of this session, presentation on space. When Dr. Karthikeyan talked about traveling beyond Earth and also the different worlds, I would like to think of my fascination as a rocket engineer. Rockets always amaze us because of not only because of its size and shape, which is very beautiful, but because of its tremendous power it generates in taking you from the gravity field of Earth to a place where it's no longer there. Today, human society knows only one way to travel beyond the Earth. Defeating its gravity is only rocket technology. And that too, what we are talking today is about chemical rocket technology. We are making use of the chemical energy of propellants and then converting to mechanical energy in form of giving velocities that take you to put spacecrafts in orbit and also take you to put crafts in other heavenly bodies. I remember when I worked with Dr. Angan on one of the talk he prepared for Indian Astronautical Congress in 2007, he was talking about human society's evolution. The way small societies, which was distributed all around the world, how they combined together to form a big society, the world which we are today. The enablers, one of the enablers when we were isolated islands was the sail ship. Now the enabler today is a rocket. For societies to mingle together, maybe 100 years from now, 1,000 years from now. That's why it is so interesting. It is not just for putting spacecrafts in orbit and do remote sensing and communication, but far beyond that capability, we are talking about rockets. And that's what is fascinating me. Of course, we are making the rockets for putting spacecraft also. Okay, can you go to the next slide? We heard about the PSLV. PSLV today is the workhorse rocket. We did fantastic missions except its first failed flight. It has been doing a consistently successful flight. PSLV represents one of our confidence of ISRO, that we are able to make rockets. We are not only able to make rockets, but it is possible to launch them, every launch successfully with precision, improved precision. And we are also working towards cost reduction, improved payload capability, etc. I don't go into all those details today. Next slide, please. GSLV represented yet another step. PSLV is capable of putting almost 1 ton to 1.5 ton class of spacecraft, which is called a medium class of spacecraft. Whereas GSLV is a little higher capacity. I can't say it's a quantum gem at that point of time. But it brought in a new technology, that is a cryogenic technology. Once you have the cryogenic technology, it gives pace way for going for much heavier spacecrafts, building, launching them, etc. So that's why I put that cryogenic engine there. This technology we harness from other sources. In fact, in the original PSLV time itself, liquid propulsion technologies were obtained from France. We worked with them and we developed an engine called the Viking engine. Both ISRO engineers and European engineers, they worked together for almost 5 years and developed that engine. And it was produced in India for PSLV and produced in Europe for Ariane 4, which they discontinued later. But when you come to cryogenic technology, we had the tie-up with the Russians where we had the technology denial. But we were later successful in converting that engineering design into a working engine, which is now flying in GSLV. After a few failures, we were able to make it successful, and last 2 missions of GSLV were successful. The next launch of GSLV is scheduled on 29th of this month. We are ready for the 3rd cryogenic stage to fly. Next slide please. GSLV Mark III is a next jump from GSLV, though it's named as GSLV, it is yet another new launch vehicle where I was the project director, now handling something else. As Dr. Angan said that I could be the mission director for this first flight, the photograph which you show here. The whole design of the vehicle is different in terms of its propulsion systems, the solid, liquid and cryogenic stages, but cryogenic was not active in this mission. But we are making it ready for the next flight. Next slide please. I'll talk about the cryogenics a little later. But if you look at the capability of ISRO in terms of this chemical rocket propulsion, in the solid motor technology, we have a capacity to build even a 200-ton rocket, or even any rocket which you want to build. Say it is a heaviest booster ever built in the world, the SLS booster. If India wants to build tomorrow, it is possible for us to build, and that confidence is that we have today. And we can also build very, very small rocket, like 50 grams size rocket, which can be put in moon mission. We use them for spinning up the craft in the moon Chandrayaan-1 mission. So the host of this range of rockets we are capable of building without any problem today. Next slide. And on the liquid engine technology is something that is very interesting, where I had that center. We have the Viking engine technology, which is currently flying in PSLV. But meantime, we were acquiring this technology from France. We were also developing engines of different class, which we are flying today in PSLV as well as in all the spacecrafts. You know, every spacecraft contains a liquid engine. Because we put them at a lower altitude, it has to fire and then go to a higher altitude called the geostationary orbit, the 36,000 kilometer. Rockets cannot put it there, so we put an engine there, liquid propellant there. So a satellite also is there is a rocket inside a satellite. So those engines are designed in India, and then we are using successfully in all the spacecraft as well. Next. The cryogenic technology is yet another complex technology that has come into us. Why I say cryogenic technology is so complex? As some of you may be knowing that we are using liquid hydrogen and liquid oxygen as the fuel and oxidizer here. And hydrogen is at 20 Kelvin. It's almost 250 degrees below 0 degree. We have to keep it at that liquid state, cooling to that temperature, and we have the liquid oxygen also. They have to be handled. And when these combine, what comes out is nothing but water. And the systems and rocket parts which are working at tremendous power of megawatt power. For example, that engine which you see here, it generates almost 35 megawatt of power in a size which I can lift myself. So you think of a generator, and you would have seen somewhere, which is a 1 megawatt generator, it must be weighing a few tons. But a rocket engine which produces that much power is a few kilograms. So it's a power-packed system. Next slide. And this is what Dr. Angan talked just now about the semi-cryogenic engine. So this is a three-dimensional view which we are now working on. We started testing its parts now, and our target is in another 1 year we will be testing the full engine. The important point is this is the first time we are making a liquid engine which is producing thrust, almost 200 tons of thrust. We have been talking about similar thrust only in solid propulsion domain till now. So first time we have such an engine. It has a host of configurations of rocket that can evolve out of it, which I will show you in another few slides. Next. Another area which is interesting is air breathing propulsion, which we heard about a little while ago. Dr. Angan talked about the reusable launch vehicle. So we have a stream of reusable launch vehicle air breathing technology coming in. We also have the semi-cryogenic technology coming in. And when we have these two technologies, it's possible to combine them and produce rockets, which can be a conventional rocket, which you call them expendable rocket. That means you put the satellite, rest of the rocket falls down and lost in the sea. And if you are able to bring the whole rocket back and then reuse them, as some of the other spacefaring nations have shown us, it's going to be very cost effective. And only if it is cost effective, we are going to use it for our day-to-day travel. We may set up our house at moon and make an occasional visit to our friends there. If all this had to happen, then the cost of launch has to come down significantly, maybe orders of magnitude. And that's possible only if rockets are reusable, like aircraft. Every day it takes off, put something, and then come back and does the next mission. When is that day going to come in rocket technology? That's what we are all looking for. And that's possible only when we have the reusable technology, air breathing technology, along with the chemical rocket propulsion work together. And also reusability has to come in a big way. It's a sad fact that today reusability has not come to a level where we can say it is economically and commercially a viable option, but days are not far away. Next. Of course, many people are working on such technologies. I just put a few slides here. On the work done by the Falcon 9 and the SpaceX is something which is very, very interesting. Those who are interested to read about them, you can know much about SpaceX work. And also the other vehicles like experimental vehicles launched by ESA, the New Shepard vehicle for the Blue Origin in US, which is demonstrating its landing capability of conventional rockets. All these are great work which is taking place elsewhere. All these are something that is food for thought on the direction of others in bringing down the cost of launches. Next. But in the meantime, Americans are working on rockets which are conventional. Much bigger, massive rockets are being built. For example, the SLS. They want to spend man to Mars and also once again explore moon. But their old rockets are no longer there. So they are working on newer rockets like the Ares 1, and after the space shuttle era, this work is now currently in progress. Next. And also bigger solid boosters are being built by others. By the Americans again. This is a photo of the testing which they are doing. Next. SpaceX, which is working on a new rocket called Falcon Heavy, which they are targeting that Elon Musk has told that I want to go to Mars. So that has been his goal, and he's developing a rocket towards that. He's bringing them down, recovering it on a sea platform, and he has even tested the recovered stage recently. So this all triggered us also, because it's not, don't tell me that we are trying to copy somebody else, but when somebody very novel way he demonstrates that there are things possible in other ways than what we do, we should also think in that direction and then see whether recovery of a rocket in the winged way is the only way, whether we can have a vertical landing and recover any of our rockets. Is it possible? This is some of the thought which is currently going on within ISRO. Next. Another interesting area which we have to work now is going to other planetary objects and then land there. Of course, we have been successful in putting moon, the first Chandrayaan flight, we were able to inject a craft onto the surface of moon. It actually crash landed there. But when you talk about soft landing, it is yet another new technology. Today we are working on engines which can be used in spacecraft, and we can do a soft landing. In another few months of time, we will have a test of such an engine, and we will be suspending that engine from crane and when demonstrating how it actually negotiates and then lands very soft on legs on the ground. So this is planned in one of our missions. Next. Next slide, please. This view graph is about that. In Chandrayaan 2 mission, we have planned to put a spacecraft with 3 parts. One is a craft which will be orbiting around the moon, and another craft which will be deorbiting and coming down and landing on the surface of moon. And after that, a small rover will come out and then explore the surface of the moon. So if you have to do that, we need to develop a host of technologies, especially in terms of propulsion and also navigation. How to negotiate that process of deorbiting and then control the thrust and then land on legs is something which is going to be challenging. And all that we are going to do in a few years of time, maybe 1 year, 1.5 years of time, we are going to complete the development of this launch. Of course, launch dates are to be announced by chairman only. Okay, next. LOX methane engine is something which is very interesting. We have taken it on a great interest which we have created within our organization. You know, methane is something which is a simple fluid, propellant. This contains only a few molecules of carbon and hydrogen. Why it is so interesting is it is possible to synthesize this chemical, maybe in some other planet. Suppose you have a source of hydrogen and carbon, it's possible to synthesize this fuel, and then along with oxygen it forms an excellent fuel which can be created on other planets. Suppose you have a rocket engine and you run out of fuel, it is possible to create that fuel there and then use oxygen and then fly back. Possibility exists. So that's the interest that we have on the methane. But methane compared to kerosene, which similar rockets work, methane is superior in terms of its propulsion efficiency, but little more space is required because it is less dense. But this engine development is something that is going on elsewhere. Those who are working on kerosene engines are converting slowly them to methane engines. We also started developing an engine of this class. What we think that once we have this capability, it will be the one which will ultimately be used in rockets that will go to space. It will be landing on Mars and then coming back. In such mission possibilities, this engine is going to help us. In another 2 years, we would like to have the first test of this engine. Next. We are also developing smaller crafts for propulsion crafts which can be put on our current rockets. Of course, you know that satellites are having engines. I told you that you put them in a lower orbit, they fire that engine and then go to geosynchronous orbit and then remain it as a communication device. Suppose you can put that propulsion into the rocket and do not have a rocket engine in the satellite. Make it much more simpler. Almost half the weight of the satellite can be used for, can be reduced, and we will be able to pack more transponders into the spacecraft in such a case. So direct injection into geosynchronous orbit is something that we are trying to target now. Why not the rocket go, do the second burn and go put the spacecraft at 36,000 kilometers itself, which actually takes almost 5 to 6 hours of flight itself. Today, each launch is only 20 minutes, but if you have to really put the spacecraft in geosynchronous orbit, the rocket launch will last almost 6 hours. So how do we handle a rocket launch in that duration, and how to put a spacecraft directly in GSO is something which is very interesting. On that we are working on now. Next. Clustering of liquid engine. This is another interesting area, which when you have bigger rockets of thrust engines of 200 tons, if you put them together, it is possible to remove the solid booster concept which we have today. It's not because solid booster is a wrong concept, but once you have a liquid engine, the advantage here is the rocket mass comes down, you can test them in the ground and then fly, because before launch itself, the engine can be fired, and we can check the health of all the engines, and if it is healthy only, we allow the launch to proceed. But such an opportunity doesn't exist in solid boosters, and they are more efficient. So, and the rocket will be lighter and it can be handled easily, and it can be throttled and we can bring it back. So all those advantages along with the clustering technology is something that we like to explore now. So towards that we are configuring rockets. Next slide. When you have the semi-cryogenic engine, we will first make a single engine stage and then put multi-engines and make a rocket, which I have shown there. We put it at 2024, we will have such a rocket. And when you have the rocket which is standing there, we will have the manned mission on top of it. Why I said that is, when you have an all liquid stage, and it is more safer for a man to ride on it, mainly because the dangers of the solid boosters are lesser. It is fully testable in ground, and then when you fly, we are sure that there is not going to be a danger. And number of propulsion stages are also lesser, which improves the reliability of the rocket itself. So this is a concept which we are trying to work out for the years to come. Next. We are also trying to develop, based on this new engine technology, a host of new vehicle configuration, as Dr. Rangad has already shown. I don't go into all those details. Next slide. Yeah, this is what I have shown, that we have the cryogenic technology. We are trying to develop the crew escape system, which is the human spaceflight safety device. Suppose in case of an accident of the booster rocket, how to save the astronaut. So this test is planned in another few months of time. We are going to put the whole craft in ground, and we are going to simulate a failure scenario. We are going to fire this crew escape system and take the craft almost 2 kilometers away from the zone of accident, so that in case of an explosion of the rocket, the astronaut will be safe. So this will be developed, and we are developing the semi-cryogenic engine, putting them together to cluster, and then ultimately leading to a rocket which will be a human-rated rocket. Next one. And while we have the human-rated rocket, we are also conceiving rockets which can be used for putting spacecrafts almost 10 tons of mass into a communication orbit. Or even you can take up to 15 tons of mass in a low Earth orbit. For example, if you want to build a space station of our International Space Station class, we need the capabilities of this type to take modules and then start building them. Or even if you want to look at generation of power from space, we need to build large array of structures. So such mass transportation is something that is required in the future. Next slide. Oh, these are all our designs, concepts, which I am not going to tell here. I only want to tell you that the basic propulsion systems we have handled on in another few years of time, we can create launch vehicle designs which can fill a range of payload capabilities from 1 ton to 15 ton. Anything that we can do. Next. Reusable launch vehicle technology, Dr. Rangad already mentioned, so I will not spend time on that. But what was more interesting here is that we were able to do this such a mission of demonstrating flight of a rocket and an aircraft combined. And understanding of such a technology of going through a hypersonic flight. You know, our aircrafts are not flying at speed faster than sound. They are flying in a speed slightly lower than the speed of sound. But this aircraft flew at a speed which is 5 times the speed of sound. So when it flies at 5 times the speed of sound, you know how the control systems which is working on the wings and the tails and take you to steer to a place, the level of understanding we are not having in India. So this we created through large amount of test. And only remember this, suppose you have an aircraft, when you test it, then you first roll it on the track, you take it to a little altitude, then come back, then next day you may take it to a little more higher altitude. But when you build a rocket, you don't have that luxury. The first launch itself will go through the entire flight regime and it comes out successfully. This is a challenge of a rocket. But this challenge is not there in an aircraft design. And that's why it is all the day interesting that whatever you are doing, you must understand 101%. If you are that extra knowledge is not there, it's going to be a failure. So the level of depth of understanding that we need to have on this is so high. Next. We are also testing an engine called air breathing engine. Air breathing engine is something that is going to use oxygen in the air and then fuel from which we are using as hydrogen. That engine is ready now. This launch will be announced. Actually, it was scheduled this month, but due to some problem that we are delaying that launch schedule, any day it may take place. This rocket is ready at Shri. What we are trying to demonstrate is when a rocket flies at hypersonic speeds, like Mach 6 we call it, Mach 5 times the speed of sound or 6 times the speed of sound, the air can be taken in without a pump or a compressor. It actually gets compressed. Then we can inject hydrogen into it and then burn it and then produce thrust. So no moving parts, simply a duct which will act like an engine. But the difficulty here is that when air is flowing at 5 times the speed of sound, how to hold a flame? If you ignite a flame, it won't stay there. You know, when a hurricane goes, how to keep a candle burning? This is a question which is being answered in this design of this engine. So we have tested in ground and seen that it works well. We are hopeful that it will come out well in the mission of testing. It produces a small thrust only, but once you have this technology, it will be possible to scale up and then make a workable engine. Next. I'll skip this next. Another interesting area we work on propulsion is the electric propulsion. Electric propulsion is a new area where we have to introduce it into spacecrafts. You know, chemical propulsion we've heard about, I told you, chemical energy of hydrogen, oxygen combustion or any chemical combustion is used. But in electric propulsion, we are harnessing the power of sun as electric power. We create a plasma using a gas, something typically, any gas can be used. Xenon is a gas which we are using here, and we convert it to plasma and that is simply ejected. It's not a chemical propulsion, it is simply a electric power is used to create plasma and that is through the nozzle, produces very small thrust. But the interesting point here is that it produces at very high efficiency, almost 10 times that efficiency of a typical chemical combustion propulsion system. But if you put them, spacecraft can be made smaller. We can put them more transponders in spacecraft, and if you use such thrusters, it lasts very long. For us, typically a 6-ton spacecraft, which we are weighing with chemical propulsion, can be built just 3 tons. And we can launch them using our spacecraft and still do the same payload missions. So that's the advantage. We are already testing them, and by December we will be launching this this thruster in one of our spacecraft. Next. This all I will skip because of shortage of time. Next. Various advanced propulsion techniques are there in the electric field and the plasma, microwave plasma. We have started many such researches in our organization. All of them are not having any immediate applications, but still they are the research fields which are very, very interesting. Next. I conclude with this slide saying that we have a host of chemical propulsion technologies, and the sustainability is something which is very, very important. There is always a question whether this is the only way you can make a rocket. Is there any other way? Of course, there is lot of discussion going on this area, but even today we know the only way to overcome the gravity of Earth today, as we know today, is only chemical rocket propulsion. So in this area, various technologies on which we have put our handle, and ISRO, we can proudly say that in all these areas, solid, liquid, cryogenic and semi-cryogenic. We are now becoming masters. Of course, we are masters in solid, and we have reasonably good in liquid. We have become successful in cryogenics, and semi-cryogenic is something that we are going to get our hands in the next 1 or 2 years. So with this I conclude. Thank you so much for the question.